long lecture today. There's nothing new technically. It's mostly just a recap, and then I want to open it up at the end to discussion and comments and whatever about the class, accolades if you have any. So final projects, again, videos are due on Sunday. Post them online, upload them to YouTube or Dailymotion, or if you want to do something else, just send me a URL. If you really don't want to put them online, talk to me earlier to make sure that we can come up with some way for you to copy it to me. And then next Monday and Wednesday, we'll watch them in class. If there's something, you know, we'll see each other's work. It's often pretty cool. It's pretty relaxed. Bring popcorn. Actually, you can. There's no food allowed. And then Thursday on the 10th, code and website or whatever write-up are due. You can do that on GitHub pages. You can make a long README or README in Markdown or whatever in GitHub. Whatever, as long as it has the sort of project description, you know, the same sort of things, sort of the introduction, the stuff that went into your proposal, the algorithms that you're going to use, how you're parallelizing them, example images, plots of timings, things like this. And then especially the introduction to the code. Yes? Yeah, whatever. As long as it's, you know, you can do something on GitHub pages that's flashy. You can look at, if you want to look at like last, 2013, I think, is the most recent projects that are linked on the, I have a link to previous year's projects from 2013, 2012. Some of the 2013 projects are still up, and you can see what they did. I mean, this should be basically in the a final report type thing, but it doesn't have to be more than a few pages, but it has to describe what you did and give us an idea how to use it. And then just send the URLs to the staff mailing list so that to make sure we have, yes?
Video presentation in class, is it just the videos being played, or are we also presenting?
It'll just be the video. So in class on Monday and Wednesday, we'll just be playing the videos. I mean, if people have follow-up questions, it's good to be here so that you can answer them. But in general, it'll just be, we'll play them and you know, I'll play them off my laptop or whatever. Yes? Like it has to be better in Star Wars. You could do your faces what? No, I would do just like a screencast. Like, I mean, it can be. I mean, the easiest thing is often just, you know, set up some keynote PowerPoint slides, and go, you know, and a script. Go through and say, here, you know, give an introduction to the algorithm or the problem, the algorithm, your approach, how you're using parallelism. If you have results already, some of the results are preliminary results. Basically just like a mini lecture about your work. 2 minutes, 3 minutes. Don't make it too long, people get bored, unless it's like explosions and stuff. But just a couple minutes, long enough to give the background, the algorithm, the parallelism, and results or hoped for results. Drawing is better than text. Talking over text is very boring. So illustrations, if you can do them. Try to be professional about it. I just say that because a few times in the past, in the class, there have been things that are obviously put together the morning of, and it shows. So anyway, any other questions about final project requirements, things like that? All right. All right, today's just a recap, right? We started off at the beginning of the class, why parallelism? Why do we care? Why is this a big deal? Why is this class? Why is this happening? Right, and we've seen this graph over and over, Moore's law, right? Ever since we started making, you know, back in the 4004 days, this nice linear plot, I mean, it's a nice linear graph on a logarithmic axis of look how many transistors we can pack into these things. And essentially the cost of something at the top and the cost of something at the bottom is the same in whatever dollars it was. The peak machine that you could ever get was always about $100,000. Back then, now, I mean, you can buy a much larger machine, but you can get a good sized cluster for $100,000. Pretty easy to throw together. Usually, you know, 100 nodes or the equivalent. Same thing at the bottom. you get the most powerful desktop. Most powerful desktop, they each cost around, somewhere between $500 and $2,000. But the number of transistors and the power, the computation that's been available to us continues to double every couple of years. Right? But for the past 10 years, right, for a long time it was salad days, right? Everything just gets faster and faster. The transistors and the performance were just linked perfectly in single, you look at the orange and the blue, the two top graphs, number of transistors, performance of those transistors just chugging along right next to each other until, the early 2000s when they separate. Because that's the single thread performance, that's the single core performance. It's still getting a little bit better. We're still managing to improve performance on single cores through out-of-order prediction and better caching, branch prediction, better compilers. But they diverged, right? And partly that's because we couldn't make the chips go faster, right? Each core, we've pushed it to the limits of silicon. It can go so fast and no faster. As they get smaller, we can't drive them as fast because crosstalk between lines, as you increase the frequency, goes up. And so we stopped going faster in around 2000. And we started having to dump all these extra transistors into more cores. Interestingly, we haven't had to use more energy. We'll talk about that briefly here. That's actually what's driving a lot of supercomputing now, is not how fast, but how cool you can do things. The primary cost in most supercomputing centers is the air conditioning, not the machines. Yes? That's just power. Yeah. It turns because as you get smaller, the energy density goes down. I forget the formula, but when you make them smaller, you need less power. So even as you pack things in lower, you can run them at lower voltages. You can run them at the same speed, but this is just total power for the chip. The other thing driving it, right? There are all kinds of things driving this, but the same thing's happening with memory. It doesn't go faster. It has only gotten, in the past 20 years, it's only gotten about twice as fast. Right? Looking at this right side, latency. This is linear. The red graph. We've gotten a little bit faster, not that much. The blue is logarithmic, and that's density. So we get more and more memory. We can hold huge problems in the memory of a single machine. We have like a giant milkshake, and we have a tiny little straw, right? We can just pack more and more of this, but we can't get to it. And when we do get to it, we need to do a lot of computation for it to be worthwhile, because every bit that we pull through that tiny straw is a very long wait. So we have to do a lot of work for it to be worthwhile, or to be able to do anything interesting. Same thing with disks. Again, they're, 80, so 30 years ago, 72 times faster, that's reasonable. 80,000 times bigger, right? So, our RAID crashed, our group's RAID crashed a few days ago. It's been rebuilding now. It's like, 30 terabytes, 20 terabytes? It's been rebuilding for like 3 days. Takes forever. Disks are slow, memory is slow, everything sucks, right? We've got all this compute, it's split into little parts, we can't just use it. Yes?
Does that include solid state drives?
Not really. This is the only one that's SSD, but it's following the same sort of path. Solid state's nice, but doesn't really improve that much, and the bandwidth is still the same in a lot of ways. The memory hierarchy. Fast at the top, small, and then it just gets bigger. Each of these should be really exponentially wider and exponentially slower, usually. All of our data, we can solve giant problems down here. We can map neural structures, we can crawl the web, and we can serve ads and whatever. But all the interesting, to get the data from here up to there is very hard. Usually what we have to do when you have a problem this large, the pipe is so thin, you have to do a bunch of pipes. You have to have a cluster of machines able to access this in parallel to be able to get the data at all. If you want to crawl the web or analyze the web graph or whatever, you need a very large number of machines just because to get this data into something that can actually process it in any reasonable amount of time, you need to do it in parallel. You're driven to parallelism not just because of the multi-core revolution, but because our storage is so large and our access to it is so small or so narrow. And so the way we fix that is we parallelize access as well. All right. So, like I said, this is pushing us towards things like this. The Harvard supercomputer cluster, the Massachusetts Green High Performance Computing Center out in Holyoke. Big systems. Again, the most expensive part of this thing is cooling, by far. Got the Intel, you've got multiple cores below that, right? Individual machines. A lot of processing power. Split up into little pieces. And a lot of this is just to try and fix that pipeline problem, right? Get us to the data. Got a huge cache. All kinds of things in here for out-of-order prediction of memory reads, trying to get the data to the processing. A lot of this class has been about where is data moving? Not what am I going to do on it, but where is it? How do I get it to the compute? How do I do useful work? How do I avoid talking to, go off chip to get memory, go to L3? How do I keep things in cache and keep it near the compute? How do I deal with the fact that when I have multiple cores, they need to talk to each other, they need to share data? These are all hard problems, right? Hard problems still in engineering for building these things, hard problems to take advantage of. Right, in the extreme case, you throw away some of that, make your life simpler in some ways by throwing away all these caches and out-of-order prediction. You get something like this where you've got just massive superscalar architectures, right? 500 cores, amazing amounts of performance, very hard to control, right? You can't do arbitrary computations on a GPU efficiently the same way that you can on a CPU because you've thrown away all of that, and now to get that performance, to get that, teraflops, floating point operations per second, you need to program this in a way that is unusual, not the normal way that, you can't read your email on this effectively. And at the extreme end, again, hitting on power, on size. And the newest, embedded computer from NVIDIA does a full teraflop, which is up there, and only consumes at a maximum 15 watts. That's like a very dim light bulb. You can hold that, right? 15-watt light bulb you can just carry around. It's not warm, even. I mean, this is very low for that amount of power. And it's really small, too. I mean, it's wall size. So this is just, what can you do with a teraflop of power that you can carry in your pocket, right? You can power off of a small battery. It's everywhere. It's from the largest computer down to your phone, right? My phone has 4 cores running at above a gigahertz. Why? Like, how do I take advantage of that? Why do I need that? How do you generate need for that, right? How do you come up with some way to use that that's interesting in some way that makes people realize that, or takes advantage of that process in an interesting way? Hopefully this class has, piqued your curiosity or your greed or whatever that motivates you to find ways to take advantage of this in that situation, desktop power, GPUs, whatever. As you've probably learned, it's not easy, right? In theory, we can do this all in parallel. We can do our work, and it's all just very easy, right? But it's not, right? Things go wrong. Figuring that out is tricky, and a lot of time it takes experimentation, right? So a lot of the homework was not do this, it'll go faster. It's do this and see what happens, right? And you've all got a bunch of different computers. Many people got different results from what we saw on our computers, from whatever your neighbor did, whoever you were collaborating with. That's fine. The point is you need to understand, if you're tuning to a particular architecture, you have to do some experimentation. You have to understand what you have to experiment with. Is it the cache? Is it memory accesses? Is it on the GPU? Are you failing to coalesce some reads? Things like this. If you're dealing with locks, are you waiting on locks? Are you waiting on global memory? False sharing? All these other problems that can happen. You have to experiment. You have to understand what's below, what's within the hardware, what's below your software, and what's going to cause it to go fast or slow. All right. We just talked about multi-threading. We've given you a hint of OpenCL and what it can do, how to use it. Some people are doing CUDA now as well. I'm a big fan of GPUs. They're very interesting architectures, and I do a lot of things with signal processing, image processing, things like that. And they're a pretty nice architecture, actually, in a lot of ways. I would have liked to have spent more time on it. And unfortunately, we didn't really have that time. But this, I think, is where some of the most interesting space is. All of the top 500 supercomputers, not all of the top 500, but the top 500 supercomputer list is, this list of who has the biggest big iron out there. It's being dominated more and more at the top by GPU clusters, partly because they're much lower power, right? So you can dump a lot more of this compute into a supercomputer center. It doesn't take as much cooling, which is the primary cost again. And partly because it works really well with a lot of interesting problems. Image processing, image and video, sound, physical simulation. You can even map some things that don't seem as structured as most image processing problems, or things that that are obvious how to map to the GPU. We saw things like, physical simulation of colliding objects running on the GPU is also possible, things like this. So they're pretty cool, keep an eye on them. If you're going to continue to do any sort of scientific programming or high performance programming, be aware of what you can and can't do on GPUs, and keep track of the literature. See what people are managing to pull off on the GPUs. It's surprising what sort of general computation is possible there. And then if you're doing really big problems, there are clusters, Spark, or MPI, or batch processing, or whatever. Be aware, though, as we saw with the cost paper, and in the homeworks itself, there's a big overhead you have to pay for using something like this, for Spark, for cluster processing, all of this. Partly because machines are even farther, memory we consider far away when we're doing computations. Other machines are really far away. But also just the configuration difficulties, the pain that you went through for homework 1. Hopefully it taught you, hopefully it taught you that you should be wary of using cluster solutions. I don't know if we achieved, they can be useful. They really can be. If you have, in many cases, if you have multiple machines, it's possible to take advantage of them efficiently. I don't think we managed to do that so much with Spark, unfortunately. That was sort of a Spark AWS problem. Don't give up on them, necessarily, is what I'm saying. All right, that's really it. That's the whole course in a nutshell. I would like now, I do have a chair. Sort of just open it up to discussion about what did people like, what didn't they like. What do you think you'll find useful? This is often an interesting question. What do you think you'll find useful going forward? And what do you wish we'd spent more time on? Or anything else?
I really like the GPU computing stuff. I do a lot of scientific computing
Excellent. Yeah, GPUs, so we use GPUs for a lot of our stuff and our research as well, and if you can map a problem onto it well, which is often tricky, and sometimes figuring that out is difficult, yeah, you're guaranteed to get something like 4 times better than a CPU, and easily, sometimes, depending on the problem, 100 times better. So it can be really nice. Wow, all of you are a lot taller now. How often do I use AVX in practice? I'm going to use it more after the class. Like, working on some of the homeworks and building those up, I found it easier to use than I expected. So I tried it out before using like SSE and things like this before, and it was just more difficult and more limited. There wasn't the energy expended to use it was not as good as the payoff. AVX, I think, has switched that. So the tools are better, and you're getting 8 times. And the new AVX, which will be twice as many registers or more. So there are a few problems that we solve that don't map to the GPU that I'm definitely going to use it soon. Most marketable languages or tools. So saying that you've used Spark will get you in a lot of startups. That said, I've seen some comments that Spark is basically like Hadoop, and it's a rat hole for startups. But knowing it and being wary of it, knowing when you can apply it is a big plus, I think. So Python is, I feel like it's marketable. It depends what you're trying to do. Saying that you know Python and have used it, particularly Python and Python and Cython together, in a lot of cases. If you're talking to a Python shop, saying, "Oh, I've done multiprocessing with Cython to get around the GIL," if you can talk intelligently about that when they're trying to do, if you're talking about performance to a Python shop, that's very useful, and that's something that I use all the time. But I'm a big fan of Python. There are other languages that do it better or more directly for multiprocessing. Saying that the multi-threading aspect is also, I think, useful. To say, okay, I've done multi-threading processing using locks. So Spark, partly just because of the buzzword, right? This indicates that you've done cluster processing. Python to show that, Python with Cython is like, I can do high-level programming, and I can dive into the details. OpenCL CUDA is not as marketable, but this is because fewer people are using it still. I mean, it's a more limited set of people or companies and groups that can take advantage of GPUs for these problems. Is that, okay. Who likes Python now? And that didn't before? Have there been any converts? Oh, that's terrible. It's because all of you already were converts, right? Yeah. Who doesn't like Python? I want to hear who likes something better, something else. It's fine, come on. I don't care, I'm going to keep using Python, but you can make other suggestions. No, nothing? No one's going to go on the line for camel or anything? Python does have, that's maybe the biggest piece of friction in the material in the class is that Python and multiprocessing is not a natural match. And so we've had to go through some hoops to get through that. But it can be. And multiprocessing is actually a pretty efficient way if you're just going to solve problems with Python. Multiprocessing can be quite effective. And as a lower overhead for getting started. Other comments? Good. I tried to do that. I decided at the beginning to try to keep some of the problems similar because I didn't want you to have to fight with the problem itself. You might also notice that problem 5 was basically the same on all the homeworks. No, not. Homework 1 and homework 3. It's all just union find. Right? One of them very slow and one of them much better. Uh, that's probably the saddest thing I feel about the homeworks is that problem is an interesting problem. The graph processing in general can lead to can be very interesting. Unfortunately, the amount of thinking to do about graph processing and the amount of thinking and typing and experimenting to do with AWS led to a bad product space. So, yes?
One thing you could consider for the next class or something, I feel like I have a really good grasp of Python, Python, and OpenCL, but I still don't feel like I have a great grasp of a low-level language like C, C++, and like navigating with the pages, as you were talking about,
Yeah.
but there were hardware limitations, as you said.
Right, trying to dive, so it'd be nice if we could dive down deeper into low-level languages and low-level behavior.
Maybe program something in C and wrap it in Python or something like that. I've done that in my own work sometimes.
Okay.
And I still don't have a good feel.
And this is, yeah, it would be nice to be able to go down into a low-level language like C, because really then you can do multi-threading. Well, you can do whatever you want. You can get, the multi-threading is closer, right? There aren't as many hoops to jump through, and it actually behaves as a multi-threaded thing. And on the negative side, not the negative side, but the lack of high-level interfaces to threading behavior can be painful. So you hit a lot more bugs that way. It's also because a lot of people, if you haven't done a low-level language before, if you don't already know C, it's hard to teach C and, I'm not saying it's not a good idea, it's just hard to teach C and parallelism at the same time, I think. It would be nice. I mean, if you do Python and are going to be writing something in a low-level language like C, my practice now is never to use C. If I have existing C, I'll wrap it in Python, but if I need a new algorithm, I write it in Python. Not because Python is better, because it's about as good, it's a little bit worse, but not having to cross that barrier. If there's one thing that I've dealt with a lot of languages and a lot of different, I used to program in Perl, and I've written in Lisp, and I worked at, I've done C and where. Not having to cross a mental barrier between C and Python is very, very useful. I mean, it's more about I'm impatient and I don't want to spend time waiting for my brain to catch up.
It's possible that if I did more C programming, I would change my mind.
Right. I mean, no, C is a wonderful language. C++ is also sort of a wonderful language. What? And it's got a Turing complete type language built into it. Anything else? Other comments? Come on, I know there are things you didn't like about the class. It won't hurt my feelings.
I would have appreciated if the homeworks were split up. So the homework seemed this big chunk of work that you had to do kind of separate from the course.
Mm-hmm.
So it felt like I had to reach back 3 or more weeks
Mm-hmm.
to understand what I was supposed to learn. So if we had spread that out through one problem, half a problem,
Mm-hmm.
have it aggregate and say, okay, go turn all these in and I'll
I see. So it would have been nice to basically hand out the homework as we went along.
Yeah, because then it would be like, okay, I learned about this in class. I want to start working on something with that, just to kind of help internalize what I was learning.
I think that's a very good idea. I think it would also then force people or encourage people more to get things going early. Right? There were especially a bunch of, each homework required installing or setting up something different. And a lot of that was pushed towards the end, which is understandable. There are other things going on all the time. And so,
If you could make this more of a chop type of approach where it's like, hey, this is what you got to do today.
mm-hmm.
You're going to be more motivated to do it, and I feel like you're going to learn it a lot faster.
Okay.
Then you're going to be using that more consistently over the course of the semester, rather than a really good sprint.
Yep.
I feel like you're good at it, and then you go from the beginning.
Okay. No, that's a good idea. I do like that. Yes?
Building on what Taylor said, I feel like that's some material after I did some homework. So like watching it in lecture, I thought I might understand it, and then I'd like go sit down to do the homework, and
Yep.
I have no idea what I'm doing. I'd go back and watch the
Okay.
I understand it. Like I almost like want to lecture after, but can't get that close.
I mean, it's, okay. That's good. That's good to know. I mean, so now that the homeworks are in place, so partly this was driven, I mean, not to justify, more to apologize, I guess. I mean, it's partly driven by Spark was new this time. I didn't want to teach CUDA because not everyone had, OpenCL is more accessible, so I had to switch things from that as well. And so we had to build up the homeworks de novo. So next time I think it'll be easier. But that's good to know. I mean, this is something that's now a lot easier to do. You know, we could just hand out the Mandelbrot problem, right? It could always be, it could even be, you know, hand out the Mandelbrot problem at the beginning, make it do, you know, every piece of every homework has, do this problem and it's due in a week, and then the rest of it comes later, right? To make sure it's set up and people are at least able to do the basics. But that's very good to know. I think that would definitely improve things. Yes? Oh, that's the other thing. That's big. I mean, almost everyone knows how to use Git, but definitely put that on your CV. Sorry. You had to email. What, were you taking classes in the 90s or something? Yeah, GitHub and Git, you know, it's painful to get started. And I mean, it's not that hard to get started. To really start digging into Git and doing, you know, all kind of crazy branches and starting to pick commits out and move them to other branches, things like this is difficult to learn, but really powerful once you get it. And it makes it very easy to, I mean, I've worked on large projects with, you know, 10 or more developers before the days of Git, and it was not good. Especially when, you know, you try to commit something and you basically have to lock, and it used to be that you would lock a file when you were working on it. You know, you check it out, and it meant like from the library. Those days are gone, and we'll never go back. So Git is very powerful, and I'm glad, that was sort of I mean, Python and Git were sort of my submarine learning things. Like, these are not related to the class directly, but good to know. And hopefully that paid off, or will pay off. Yes?
Yeah, I noticed lots of like one-off have takeoffs for CS system. So like for a lot of them like come from different backgrounds. So at the first of class I was like super struggling. I know some of our classmates like from very professional areas.
Yep.
So they come to class are very easy to follow. But I was struggling at first, then I couldn't just keep up. So I feel like our class, our homework might be designed as like maybe starting from like the transition, like warm up, then go to like harder features. For example, I was super struggling for the Spark for a long time. Then homework file was like so easy, so it's like we could have done like warm up thing first, then move up to Spark. I learned a lot of things from Spark homework.
Okay.
But maybe like warm up a little bit, then
Yep.
strong.
And this is sort of a, there's a balance here between computer science course as grad student, which was, yeah, there needs to, I think also the CSE program needs to put in place some early introductory material outside of the classes to get people spun up too as well, which I don't think they did this year, but I'm really pushing for as well, yeah.
Yeah, I agree with that really strongly. I mean, I think this class is a really broad audience. Some people, I guess, have PhDs. Makes sense. For some of us, this is our first university level CS class.
Right.
And so I think almost every lecture I walked into, like I had walked in an hour late.
Oh, me too, don't worry.
So understanding what was going on even just a very basic conceptual level is often really challenging with such a limited background, terminology, or even how do you visualize what data is describing was something that I found very
I tried to build in more background material as I went along, as I found out about this, because I wasn't aware at the beginning that a lot of people were, you know, taking this as a first CS course or first course CS.
the problem with the class was the trying to be sort of swinging between people, or that maybe it's not the right class for our programs.
Yeah.
I feel like we could have like some reading materials later on.
would love to give slides beforehand, but they usually don't exist until the morning of, so all the way. I mean, I was also rewriting all the lectures as I went along. So this is the first time I've taught this class. I TF'd it 4 years ago, three years ago. But I had access to the previous lectures, but I had to rewrite most of them to match. So yeah, now it's established. Hopefully that could happen more easily.
Yeah, just building up this, one thing I found challenging, was like, you know, I've been working with computers my whole life, and I sort of knew the hardware, but like, you know, the first couple of weeks and very hardware focused, and I didn't exactly know precisely what all the words meant.
Mm.
I didn't understand the idea of types between different systems and stuff. And maybe just like, you know, a bonus lecture or something given by a TM about just basic hardware or something would be great for people that don't exactly. You know, I'm in a PhD program that isn't TM, so I picked it up as we went, of course.
So yeah, I think so. Yeah, the lectures are very much centered on how does the hardware behave. And so not being familiar with the hardware, you really, it can't be an architecture course, but and it can't require an architecture course beforehand, but it would be useful to have a mini architecture, you know, 2 or 3 lectures. I think that would be useful just to give an idea of even just like I mean, a lot of the architecture is driven by sort of past mistakes, right? The 8086 is still basically you know, our fastest computer is still trying to basically emulate almost an 8086. It's really, I took a very good architecture course, and it was basically like, okay, here's the 8086, and here are all the mistakes that we've made, all the mistakes we made there are now baked into hardware, and now everything forward has to keep on trying to fix the mistake, you know, basically paying for the sins of the past. You know, things like the Spark, Sun Spark, not the RISC architectures and things like that, were attempts to jettison that, and they all failed because it was just too widespread. We're all infected with this horrible zombie virus, and now we have to eat brains to keep from becoming, you know. Please. Okay. 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 Yeah, sections would definitely go on the list. No, not anymore.
But don't rely too much on section. Like last year, like there were sections, and some of them were like really bad at first class. Like they were relying too much on sections, and like TF, like it's not their job, so they're doing a poor job in like sometimes in teaching, and so don't do that.
Okay. Okay. You two should fight. And then whoever wins. So it would be good to do something with machine learning. I'll have to think about how that could fit in. That's definitely sort of a OpenCL targeted sort of thing. It's hard to do something, I guess I thought about that, but I rejected it possibly because you don't want to get I don't want to go too down into the weeds of machine learning, but also then when you actually use a GPU for machine learning or something like this, you're going to be using the most highly optimized libraries from NVIDIA or Google or usually just from NVIDIA, where they've handcrafted this to do the machine learning stuff that you're going to do. And machine learning in a lot of ways, well, deep learning in particular is turning into this sort of bolt fast pieces together approach. You know, you just keep on stacking them and making them wider, which is unfortunate because I think it's pulling away a little bit from the research, but also interesting because the results are very good. But I would like to do that as well. I'd like to put some machine learning in someplace. More comments? Well, I curve the final grade. It'll probably be something of a regularized curve, right? It'll be somewhat based on, everyone else, and partly based on just expectations of, just linear expectations. Okay. I mean, I could go with like the 70s curve, right, where it peaks around the B. No. Those days and the days of single core processors are all gone.
But the final project is like it's hard to know like who we should talk about, like who we should talk to.
Who you should talk to about,
Like if we have an issue.
I mean, TFs, and feel free to talk to, just mail staff if there's an issue, or yeah, easiest is to contact her directly. I have like 5 meetings after class today with different people who've contacted me. I don't have to make any more slides, so I have a lot of free time. My TFs are doing the grading, so I don't have to contribute to that either. So if you need to meet to discuss final projects in the next few days, send me email. I can schedule, very easily half hour to talk about projects. If you want to have a couple meetings before it's due, that's also fine. If you want, you can meet with your TF, you can meet with me, whomever.
Sorry, 2 questions. So how polished does their final project have to be?
How
Their code is decent, but it's not like perfect.
How polished should your final project be? It would be nice for us to be able to look at the code by inspection and see that it maps to what you said you're doing in your write-up, right? If we can, so polished, put comments in, right? Especially if you if you have a write-up and you have comments and they have phrases in common, or step 2.3, we do this. Step 2.3, we do this. It's fine. It's perfect. I do this all the time. Right? It's just like comments in the homeworks makes it easy for us to grade. So I would polish it that way.
Okay.
You may not have time to make, a nice object-oriented interface, blah, 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 blah. It's fine. Don't do that.
Okay.
Much more just make sure that we can navigate. And
And are we going to get our, sorry to bother you, but the grades on the homework before the project or something?
we hope so by the end of the week, end of the week-ish. They're chugging through.
Okay.
1 and 2 by the end of the week, and then homework 3 hopefully before the beginning of next week. Homework 1 was painful to grade as well as to do. So, yes. For the final project, can you submit IPython notebooks? Yes, that's fine. Especially for the write-up, that's a great way to do it, is to show, if you have the code and here's our IPython notebook showing how to use it. That's fine. If you submit an IPython notebook, if you've got enough text in there and explanatory material, if you want to inline your explanation and write-up with the actual work, that's fine. That goes to the same thing. Commenting in code, that's the same, that's just integrating together. I'm a big fan of IPython notebooks. We didn't use them because I would have liked to use IPython notebooks, but there's no way on GitHub to use the feedback. You can't do feedback inline on IPython notebooks. And so we couldn't do the peer review. What did people think about peer review? Good? Bad? Anyone bad? You didn't like it? Oh, you forgot to do other people's. Yeah, it's a problem. So we wanted, so there is we did want to make sure that multiple people were looking at multiple people's just to spread out the work, but also to spread out, there's the whole open source statement, which is a lie, which is that given enough eyes, all bugs are shallow. That's not true at all. But there was that problem, and there was really no way around it. If someone gets there and sees something and says, that's a good way to do this, and I really like how you did this, the next person is going to be like, it's like the guy who jumps up in basketball and grabs the rim after the basket's gone in. Like, hi. It's fine. Yeah, there is that part. Maybe next time we'll assign one person and really hammer on it, and then assign another person afterwards to. Maybe you could, we could have, okay, you peer review the peer review, or something like this. All right, it seemed like most people liked that though. I feel like it was useful. It was definitely useful to the TFs. I think it was also useful to, many people said I saw something interesting from the peer reviews, so I like.
Also useful to learn how to work with GitHub.
Okay.
But I didn't know you could make line comments.
Excellent, excellent, that's good, good. Yeah, I mean, so a big part of, I mean, if you go into software, a big part is dealing with other people's code. And hopefully you've learned two things. One, how to deal with other people's code and understand it. And two, how to make it nicer for other people to deal with your code. Right? The pain that you might have gone through in doing peer reviews hopefully inspires you to make it easier for someone else later. So, anything else? All right, thank you. Oh wait, I have another slide. Thank you, especially especially to the TFs who did a lot of work, especially Adi, who did a ton of work. He's the person who basically would look at the slides the morning as I was writing them and make sure that I was making at least some sense. Jackson, thank you for the video recording. And all of you, I hope you enjoyed the class. Hope you got useful material out of it, and I hope it pays off in your future work. Thank you again. I'll see you Monday. Well, I'll probably see many of you before then, but Monday we'll watch videos and talk about projects. Excellent. Have a good weekend.